This slide introduces the broader interpretation workflow. It emphasizes four major purposes: understanding lithology and formation evaluation, evaluating porosity, evaluating fluid saturation, integrating log data with other data sources. This is a very strong summary of what well logging is really for. Logs do not exist just to create curves. They exist to support reservoir characterization. By integrating multiple logs and comparing them with seismic and core data, reservoir engineers can build more reliable subsurface models. This is where well logging becomes central to field development planning, reservoir management, and production optimization. This slide emphasizes four best practices in log interpretation: understand the tool physics and limitations, integrate different logging measurements, calibrate logging data, use computer modeling. This is excellent professional advice. A single log cannot provide a complete answer. Every tool has limitations, and every environment introduces uncertainty. Good interpreters therefore combine logs, calibrate with known data, and often use forward modeling or computer-based interpretation to validate results. This is a very mature message for students. Log interpretation is not curve reading alone, it is an integrated scientific and engineering reasoning process. This slide is a transition toward practical applications. Here, you can tell students that by combining lithology logs, porosity logs, and resistivity logs, we can estimate the main reservoir properties needed for hydrocarbon evaluation: net reservoir thickness, porosity, hydrocarbon saturation, and fluid contacts. This is the point where well logging becomes economically important. The interpreted log suite is not only used to understand geology, it is used to estimate what portion of the formation may actually be productive. This slide introduces the concept of cutoffs, which is critical in reserves evaluation. The idea is that not every porous interval contributes meaningfully to production. A cutoff defines the minimum acceptable value of a property, such as porosity or hydrocarbon saturation, for that interval to count as productive net pay. This is very important because reserves calculations depend on net thickness, porosity, area, and hydrocarbon saturation. If low quality or non-productive rock is included in the pay interval, reserves will be overestimated. So cutoffs are one of the key steps in translating log data into realistic engineering and economic decisions. This slide introduces formation continuity and the use of fence diagrams. Gamma-ray logs from multiple wells can be correlated spatially to trace clean sand bodies or other stratigraphic units between wells. Fence diagrams provide a three-dimensional way of visualizing this continuity. This is very important because one well only tells us what happens at one location. Reservoir development requires understanding how layers continue, pinch out, or change laterally between wells. Log correlation is therefore one of the major tools for building reservoir architecture and stratigraphic models. This is one of the strongest practical interpretation slides in the deck. It explains how a combination of logs can identify an oil-water contact, or OWC. In the example, SP indicates a permeable formation over a broad interval, but resistivity drops in the lower part of that interval. Since lower resistivity suggests higher water saturation, the OWC is interpreted between about 8,540 and 8,550 feet. The slide also reminds students about gas effects. Gas increases apparent density log porosity and decreases neutron log porosity, creating crossover. This slide is excellent because it shows how lithology, porosity, and fluid logs are integrated to identify both reservoir interval and fluid contact. This slide is conceptually very important. It shows 3 scales of subsurface information: centimeter scale from core meter scale, from electric logs to decameter scale, from seismic. This is a beautiful summary of how subsurface characterization works. Core gives direct but sparse detail. Logs give continuous well scale information. Seismic gives field scale structure. None of these replaces the others. They are most powerful when integrated. This is one of the major ideas in petroleum engineering. Every dataset sees the reservoir at a different scale, and reservoir understanding comes from combining those scales. This repeated outline slide marks the final section of the lecture. At this point, it is helpful to remind students of the flow. What well logging is. Logging environment matters. The main log families, how logs are integrated for reservoir description. Now we are ready to summarize the key ideas and test whether students can read a combined log suite in a practical way. This slide lists 4 central questions. What is well logging? What is the logging environment? What are the types of log? What are the principal applications of common well logs? A strong summary answer would be well logging is the depth-based measurement of physical properties in and around the borehole. The logging environment includes borehole shape, mud cake, invasion, flushed zone, transition zone, and uninvaded zone. Common log types include lithology logs, porosity logs, resistivity logs, and specialized logs such as imaging and dip meter. Their main applications are lithology identification, porosity estimation, fluid detection, formation correlation, net pay definition, and reservoir characterization. This slide is the backbone summary of the whole week. This is a very good interpretation exercise for beginners. The slide asks you whether the colored boxes correspond to shale, sandstone, hydrocarbon zone, brine zone, gas-bearing zone, oil-bearing zone, or water-filled zone, based on gamma ray, resistivity, and porosity logs. The provided interpretation is shale at around 7,000 feet and 7,250 feet, indicated by high gamma ray clean sand between about 7,050 and 7,150 feet, indicated by low gamma ray gas from about 7,050 to 7,100 feet, indicated by neutron density crossover oil from about 7,150 to 7,200 feet, where resistivity is moderate and crossover is absent. Brine or water-filled zone from about 7,200 to 7,300 feet, where resistivity is low and water saturation is higher. This is an excellent slide because it trains students to integrate log responses. High gamma ray suggests shale. Low gamma ray suggests cleaner reservoir. High resistivity suggests hydrocarbons. Low resistivity suggests brine. Neutron density crossover suggests gas. Similar neutron and density porosity with moderate resistivity may indicate oil. This is exactly how practical log interpretation begins. You can see the detail answer here. This slide previews the next week, Reservoir Engineering, 1 Rock Properties. That transition makes perfect sense. After we learn how to identify lithology, porosity, and fluids from well logs, the next natural step is to go deeper into the rock properties that control reservoir performance. So week 6 gives us the measured and interpreted subsurface picture at the well scale, and the next week we'll use those rock properties more explicitly in reservoir engineering. This is where petroleum engineering becomes increasingly predictive, from identifying the reservoir to understanding how it will perform. Thank you everyone for your attention. This week we studied the fundamentals of well logging, the logging environment, the main types of logs, and how multiple logs are integrated to describe lithology, porosity, fluid saturation, and reservoir architecture. We also discussed cutoffs, formation continuity, fluid contacts, and the importance of calibration with core and other data sources. The most important takeaway is this: well logging converts the borehole into a continuous measurement window into the subsurface. When interpreted correctly, logs allow us to move from raw physical responses to a much richer understanding of reservoir quality and hydrocarbon potential.